Hello, Ed. This is Glenn. These are the multimeters. Here I'm setting them to read direct current volts. That's what you want, I think. This would be alternating current. This is an auto-ranging device, so notice right here it says millivolts. When the volts are higher, it will change by itself to volts. All right. So the black goes into the COM port, and the red goes into the V port. Now, this is for measuring the volts. And to measure the volts, it's very easy. Of course, you just put the two leads on either end of the thing that you're trying to measure the volts of, whether it be a battery, such like this one. Okay, so this is about 1.5 volts, or it could be something else, a light bulb or whatever you want. Now, to measure the current, the amperes, is a little different. To measure the current, it is not an easy thing. So you move this to the ampere side, but before you do that, you got to turn this off. Sorry. Right, so you turn this off, and then you switch this to, now, I have brought for you some of these D batteries because 1.5 volts is enough to copper plate a key, and the D batteries give more amperes, more current than the smaller batteries, even more than the 9-volt battery, I think. But I'm going to switch this to milliamperes. To milliamperes, it's either direct or alternating current, it doesn't care. So this is harder to, the amperes are harder to measure. You cannot just, you might already know this, so please excuse me if I'm just giving you information that you already have, but just in case you forgot, you cannot just expect to measure the current by doing this. In order to measure the current, you have to put this in the place of a wire. So this whole multimeter has to be your wire, all right? So here's what I'm talking about. So if you have a circuit here where this is going to the key or something, and on the other side, all right, so I have a plus and I have a minus. I'm gonna leave you these alligator clips. You have a bunch of alligator clips in your Idea Lab, but I think it's best if you use your own. I mean, if you use mine. And the reason is, what if somebody forgets to put them back in the Idea Lab, right? And stuff gets mixed up. So, suppose you have your key, right? And you are attaching the negative electrode of the battery to the key. So this is attached to the key, and this here, this positive part, is attached to the source of copper. So you have a copper strip somewhere in your cabinet, probably in the cabinet that's labeled metals. So this is attached to the copper strip. So you have this complete circuit. Electrons coming out of here, going into the key, and then collecting copper 2+ ions right there to become copper, just neutral copper atoms on the key. And then while that's going on, you have electrons coming off of your source of copper, your little your solid strip of copper, electrons coming off of there and going this way so that they can go into the key. And the copper atoms in the piece of copper that you have is losing 2 electrons to go up in here, and when it loses 2 electrons, it joins the copper 2 sulfate, the copper 2+ ions in the solution. So this is a complete circuit, but to find the current, you have to break this circuit, right? And you have to put the multimeter in place of a wire. So this wire is not going to be stuck to the battery itself now. This wire, this part that is supposed to be attached to the source of copper, instead of being attached to the battery on the other end, it will be attached to the multimeter. And this other end of the multimeter will be attached to the battery. You can use another alligator clip wire to attach this to the battery. So you see, measuring the current requires the multimeter to be integrated into your circuit instead of just being an absent bystander. I mean, just being an uninvolved bystander, just testing the voltage in any part of your circuit. You have to actually break your circuit and put this guy in it through these leads, all right? Then you will see the amperes. This is auto range. Well, the amperes are not auto ranging. So With this guy, I think you're going to be satisfied with the milliamp setting, but if you find that it's a few hundred milliamps, you might want to switch to the amperes. I'm pretty sure you're not going to get 1 ampere from here. I think it's a few hundred milliamps, maybe 100 milliamps. So I think you'll be good with the milliamp setting. Okay. So so I'm going to leave these with you. I'm going to leave several of these with you, and I leave several of these with you not because I want the students to be able to add voltage, but because I want the students to be able to add current. So 1.5 volts is all you need. Any extra voltage is wasted. Nothing additional happens. The key does not get copper plated any faster. So if you add batteries this way, if you put together these things, you can add batteries in series. Of course, that's going to be adding the voltage, not the current. Useless. So, but if you add the batteries this way, then you will not be adding the voltage. It will still be 1.5 volts, but you'll be adding current. So that might make the keys get, this is supposed to fit snugly in here. Sorry, this is supposed to, I'm doing this with one hand, so, okay, there we go. So that will get you some more current, more amps, more amperes. And then you just put them in like that, and then you just connect this lead and this contact and this contact to your multimeter and to the alligator clip that holds your key, and then you will be good. If the multimeter gives you negative milliamps, that just means that your black and your red are switched, so you should just switch them. Or you can just ignore the negative sign. It doesn't hurt the device to run current backwards through it, giving you negative milliamps. It's no problem. Okay? So that is for your brass key. Now I noticed that it's hard to find your copper 2 sulfate, and usually we do the copper plating experiment with copper 2 sulfate. However, you have a lot of copper 2 chloride, so I suggest you use the copper 2 chloride if your students have trouble finding the copper 2 sulfate. This is okay to use. But there's something that you need to know before you use the copper 2 chloride. The chloride ions are very good at penetrating aluminum. So usually, like if you mix copper 2 sulfate with something that's aluminum, nothing happens, because although the copper 2 plus ions want to get reduced by the aluminum atoms, there is an aluminum oxide coating that's almost invisible on any piece of aluminum. So the copper 2 plus ions can't get through. But copper 2 chloride is totally different. The chloride ions somehow make it possible for the copper 2 plus ions to have access to the aluminum atoms inside the piece of metal. And so anything aluminum will start to dissolve. So the aluminum will get oxidized to aluminum 3 plus, and the copper 2 plus ions will get reduced to just pure copper, and you're going to see copper forming at the expense of aluminum. So what that means is, if you let when you do the copper plating, you're going to make a pretty concentrated solution, maybe 1 molar, maybe more. So if you let any aluminum foil touch that aluminum foil, not within seconds, but within minutes, is going to disintegrate. Another thing, these leads, these alligator clips, they have a lot of aluminum in here. I mean, I'm not sure. They may even be just aluminum or some alloy that contains plenty of aluminum. They also have iron in here. So I think they have iron. But either way, both of those things are more reactive than copper. So that means if copper 2 plus comes into contact with the metal surface of this alligator clip, then this is going to start to corrode. So it's important. So if this corrodes, the bad of this, I mean the disadvantage to your students if this corrodes is that corrosion here is happening instead of copper plating of the key. So these are cheap. I don't really, nobody's going to cry if these get ruined. But the thing is, if these are in the solution with the key, instead of the key being in the solution just by itself with this part gripping the key someplace out of the solution. If these are in the solution, then you're not going to be plating copper on the key. You're going to be corroding this guy instead. And then all the amps that you run through there are not going to be putting electrons on the key and copper atoms on the key. So if you have your students use Faraday's constant to calculate how many grams of copper are going to go on the key, you're going to get the wrong answer because corrosion is happening here instead of copper being plated on the key. All right, so just watch out for that. Don't let the alligator clips touch the copper 2 chloride solution. Okay, so I'm going to put your solid copper 2 chloride back. Oh, if you have a student who wears iron or aluminum jewelry, please ask them to remove the jewelry before they handle the copper 2 chloride solution. Copper 2 chloride solution, surprisingly, is not very toxic. Copper is supposed to be a heavy metal, but somehow it doesn't irritate the skin much at all. But it will mess up their jewelry if it splashes onto them, especially the concentration that you're going to use for the plating of the key. It's 1 or 2 molar, maybe more, something like that. Here I have your double replacement reaction and solubility rules reagents and spot plates. All right. I encourage you to have the students mix them in more combinations than what you see on the worksheet attachment that I sent. I might have some chemicals here, such as aluminum nitrate, that do not appear on the worksheet, and some chemicals that appear in the worksheet might be missing here. My prejudice is that I have more chemicals here, such as barium nitrate, than what it appears on the worksheet. So students will have an opportunity to mix more chemicals. Now, some of these chemicals might be old, and they may have oxidized or done some spurious reactions while I have had them. So I encourage you and your students to try these out tentatively and compare your results. So the worksheet that I sent you asks you to make some solubility rules, like are all nitrates soluble or not? Are all chloride soluble or not? What are the exceptions? But I encourage you to compare your rules with some published rules, which you would find in the textbook or just on Google. I really prefer Google over any textbook, just because it's just so easy to find. With the textbook, you got to use the index, and then you might find the wrong page. So Google is just much easier. So it's important to have the students compare their results with any set of solubility rules that they may find on Google, preferably from a .edu site. Now, what we have here in these bottles are some reagents for single replacement reactions. All right. So what I've got in here is some iron 3 chloride. As I mentioned to you before, some of this iron 3 chloride has precipitated as iron 3 hydroxide or iron oxide at the bottom, but the homogeneous solution that you see at the top, that is concentrated enough to do whatever single replacement reaction iron 3 plus ions are going to do. And then we've got some acid here. There's a single replacement reaction with the acid and some metals, not all metals, but your kids will find out which metals will do that. Here we have magnesium chloride. Now notice there's magnesium hydroxide that has precipitated out, but the magnesium chloride near the top is concentrated enough to do any reactions that magnesium 2 plus ions are wont to do. But I gotta say, magnesium 2 plus ions are not wont to do, they don't want to do a lot of reactions. Because magnesium is so reactive when it's in the ion form. I'm just happy like that. So here I have some deionized water for the wash bottles. This is one of the wash bottles. There's a lid in here for the wash bottle. Here I have copper 2 chloride. Didn't really need to bring this, but you could use this if you want. This is for your single replacement reactions. You have copper 2 chloride in the cabinet marked halides over there, but you might want to use your copper 2 chloride for your brass key copper plating experiment there. We've got these spot plates for you. These are good because they're transparent. The reason why you want a transparent spot plate is because when your kids do a reaction here, if there's a dark precipitate, then it's easy to see because you just put this on a white piece of paper or you put it on a white tile and you can see the dark precipitate. But if there's a white precipitate, you put it on the black table surface and you could still see the white precipitate. That's why I like to use the transparent spot plates. Now, if for some reason you don't like how deep these are, you can use the black spot plates when kids suspect that there is a white precipitate, or you can use a white spot plate that's ceramic if kids suspect that there is a dark precipitate. Right now, the disposal of the chemicals is a little important because I have some reagents that are toxic. So barium nitrate, any dissolved barium, such as barium nitrate, is toxic. It's supposed to cause cancer or something. And then lead, I think I have lead nitrate in one of these bags. The lead nitrate is obviously toxic. It causes, I think it's supposed to cause developmental neurological damage, which might be critical at a school. So kids need to wear gloves. Let me check to see if you have gloves here. Okay, I don't see, oh, I do see gloves here. So you have gloves here. So please have the kids wear the gloves if you're going to deploy those bariums and those leads. All right, now, the disposal of the chemicals, if you